Okay, someone of you started to ask about the date of the exam. So at the moment, for sure, you have this date, two in June, one just after the course, 19, and two in July, one here and one at the end of July. There should be a light here, but
it's not like that.
So, for sure, this 4 date, I hope to add at least another one. You will receive a doodle, so you can register for the exam. You can register to only one date in case you wanted to change, you fail, you reject the vote, you can add another one. So, okay, you cannot register at the same time in two positions, just one. If you fail, you can register to another one, and there is no limit to this.
C'è una scadenza per scegliere?
No, there is no deadline. You can do it till the end. I usually have 10, 12 positions per day. It's an oral exam, so I cannot do more than a given amount of positions, say 10, 12 positions. So when the entire day is full, you cannot register anymore. So it's better to do it a little bit before. And if you plan not to attend the exam because you arrive too late, just remove your name so you leave the place for another.
I think that we are more than 40 people.
Yes, for this reason I will add some other date, but these are for sure the exact one. And yes, for sure. Any question on this? I will set up the doodle in probably in 1 week or 2. And I send you the link for the if I see that some date fill up quickly, I add another one immediately, maybe the day, the next day, so you can have one. In my experience, the problem of give you such a flexibility is that people start immediately to fill the first day, and then approaching the date, people remove the name from here and put the name here, and then shift toward the end. And at the end of July, everyone asked me, oh, please do an exam in August. No, so organize yourself a little bit. And I will use the same technique in September. So in September, you have at least 2 dates, at least, if not 3. From the beginning of September to the end of September. You have this is just to organize the exam, but you have to register on the official website. Don't forget to register, because otherwise I cannot register your vote, and it's a problem. Okay? We will discuss about the exam further. Leave me another few days for the correction of the mid-term exam. So, no question for the previous topic, isolator, circulator, magneto-optic. Did someone try to read the paper on the non-reciprocal device isolator of science and nature, or not? Someone curious of this strange grating, lossy grating? No. Okay. So you have no question on the previous topic?
Yes.
I guess. One. Yes. Right.
I didn't because on the
No?
the drug graphite is explained with delta n with
Yes.
we didn't
No.
produce the visibility at all. So how can I relate the visibility delta n f?
Visibility equal to 1. I simplify the in optical fiber, the bright grating is written with UV light, and UV light change permanently the refractive index if you have germanium doped silica. That is the core. The cladding is not germanium doped because the refractive index is lower. So if you have a fiber, basically this is silica, or silica with bows of phosphorus, some material that decrease the refractive index, while in the core you have a germanium doped silica. So if you shine the light here, because you shine from outside, so you illuminate the entire cross-section, the cladding and the core, you have basically a change of the refractive index only in the core, not in the entire cross-section, because here there is no germanium and you cannot change the refractive index. So the mode extend also in the cladding, so you do not change the refractive index everywhere, but only here. So it's only a portion of the mode that see this change of the refractive index. So in the theory, on the notes, people put a visibility in front that is a coefficient that is between 0 and 1, and is close to 1, and depends on how much the mode is confined in the core. So the confinement is very strong, the visibility is almost 1, and if it is very weak, the mode is occupy also a lot of cladding, and the visibility is a small number. But this is just a small correction of the delta n that is not really does not really affect the entire theory and the result. So we use the delta n, that's all. Any other question? So now we move to another very important chapter of the course, that is the modulation or modulator. I would like to switch on the light here, but I have no idea. Do you have an idea of? Yes, here. So the modulator is a big, long, complex chapter, but we do just some modulator, not everyone, not. So the modulator permits to, let's say, load the information on the light. If you have to transmit the light, you have to transmit the information, you have change something of the light in order to receive the information on the other side. So what to change? You can change the amplitude of the light, or you can change the frequency, or you can change the phase, and the polarization. So you need a device that is called a modulator that is able to receive your information, and typically is an electrical signal, a signal that arrives from at the level of electrical signal, and transfer this information on the light. So transfer to the light means a change something of the light, and these are 4 parameters that you can change of the light. So it is a sort of, let's say, box called modulator, receive the light from a laser, has an output to send to the link, and receive an electrical signal that is the information or the data that you have to transmit. This is a very general description, very broad description of our device. We can have 2 kind of approach. One is a laser, a fixed laser, that emit a given amplitude, given frequency, given polarization, and the light generated by the laser entering the modulator and exit modulated on the other side. Another possibility is to have a laser that accepts some data from outside, and so generate a modulated light. This is called a directly modulated laser. Directly modulated laser. These are the classical 2 approach. Also in this case, the data is an electrical signal that arrives to the device. So these are the 2 approaches. The second one, the directly modulated laser, DML, is, well, from this sketch seems much better because you have just 1 device instead of 2. You don't need a modulator. You directly change something of the laser. So the laser is an active device, and need a current, usually is a junction, so you need a current, so you can change this current according to the data, and so you generated a modulated light. So this is very compact solution, seems very easy to do. the problem is that a laser generates, let's say, a good light, stable in amplitude, stable in frequency, stable in polarization, does not change in time, if he do his job. So if you define the working point of the laser, you can generate a very stable light. If you add the modulation, so you change the current, for example, you change the temperature, it changes something, change the intensity of the light, change the frequency, change the phase, but it's not so stable as a fixed laser. With the first solution, instead you use a laser and you decide the working point of the laser do his job, generate the light, CW, not modulated, absolutely stable, absolutely constant, and then the job of change the light is done by someone else, the modulator, that has the job to modulate the light. So every time you divide the two jobs, the two devices work better. So the first one is typically used when you need a very high quality signal. So for example, for telecom, long distance telecom, is better to have a very nice input signal. Nice signal to launch in the link means always with a very well defined frequency or wavelength, the shape of the pulse very well defined, constant polarization, etc., etc. No phase modulation in case of amplitude. Well, the second one is simpler from a device point of view and can be used every time you have a short distance communication or let's say a low quality link. These are the main reasons. Then you can think to a laser that generates just one wavelength or generate multiple wavelengths. This is another typical example. If you have a multi-wavelength laser that generates not just a single wavelength, but usually it's a combo of wavelength, and then you can think to split this one with the multiplexer, for example an AWG. So you have one wavelength per output of the AWG. So here you have all your wavelength, here you have just one wavelength, and you place a modulator for each output, and then you multiplex again with another AWG or free resonator or whatever you like, all the signal together. So this is a WDM transmitter, and here you have all your wavelength generated by the multi-wavelength laser, each one modulated with a different data because the data is different for every modulator of this transmitter. So this scheme with respect to a scheme with several lasers, one laser per wavelength, one modulator, and then the multiplexer has the advantage that you have only one laser. So there are many kind of combination of laser and modulator depending on the application. you have always to think to submarine system is on the extreme on one side, very high quality signal are required, and on the other side, a data center. Very short link, where the importance is the very low consumption and very low cost and massive integration of devices. So, we will not study the directly modulated laser because we have to really to go inside the laser itself, and it's not one of the topic of the circuit, but we will consider the modulator. So we assume to have a laser that generates light, very high quality light, and we have to modulate the light. Now, the modulator has an optical input, optical output, and an electrical input. And usually this electrical input is at high frequency because you want to modulate at high frequency the light. So it's obviously there is an electronic driver here to generate the signal, but this signal are in the microwave field. So inside the modulator there is the optical domain and the microwave domain, and the two must in some way interact because the microwave modulates the light. So this is one of the topics that we will touch. I cannot go too much in the detail of the microwave field, but the electrode of the modulator are really very important, and we will study the electrode and the interaction between the radio frequency, the microwave field, and the optical field. Interaction between optical field and microwave field, so the interaction between two waves occur across the material. You cannot change the characteristic of a wave through another wave. The wave does not interact, you know. So you have to pass it through the material. So the only way is to change the characteristic of the material with the microwave signal, and the light experience this change of the material and is modulated. So we need a material that is some way sensible to the electrical field, the microwave electrical field. I'm touching all the topics that we have to study talking about modulator. Then we say that we change something of the material, so the light experiences this change, and you generate a modulation, so you change something of the light. So there are mainly two change of material, two possibilities. One is change the refractive index. So you apply electrical signal and you produce a variation of the refractive index that is proportional to the, let me say, voltage. We will never use the voltage, but just to understand, to the voltage of the electrical field. If you change the refractive index of the material, it is clear that you change the phase, because the phase of the light that travels inside the material is proportional to the refractive index, so the variation of the refractive index and the length of the material itself. So if you are able to have a material that changes the refractive index according to the applied voltage, then you can have a variation of phase, so a phase modulation. This is the most natural idea of modulation. No? So we know that this signal, electrical signal that arrive is at microwave regime, so gigahertz, tens of gigahertz, hundreds of gigahertz. And so the reaction of the material to the voltage must be very fast. So we need a material which refractive index depends on the applied voltage and react very quickly. Okay? Very broad introduction, then we will go on more into detail. As you know, it's possible to convert a phase change into an amplitude change. Think, for example, interferometer. If you change the phase of an interferometer, the arm of the Mach Zehnder, the length of the ring of the length of the ring, or another interferometer that you know, you generate a variation of the intensity of the arm. So amplitude. Think, for example, a Mach Zehnder with the two arms, a balanced Mach Zehnder, and you change the refractive index of one arm with this technique. Here, the interferometer convert the variation of phase into a variation of amplitude. The output amplitude is the cosine square of the variation of the phase, etc., etc. So if we have a material that has this property, we can use it to make a phase modulator, but also an amplitude modulator. It's a little bit more complex. It's not just a piece of material with an applied voltage. You need to build a circuit to convert the phase into amplitude. Okay. We can change the amplitude even if the absorption or attenuation of the material is proportional to the voltage of the signal applied. So if we have a material which has absorption depend on the electrical applied field, electrical signal, or this goes directly to an amplitude modulator. So once again, this must be fast, react very fast to your signal, change quite a lot the intensity, the absorption. The material that has these properties are called electrorefractive. This is property electrorefractive material. And the other case is an electroabsorption. Or electroabsorptive material. So if I have a material with the first property or the second property, I can do a a phase modulator or an amplitude modulator or use a circuit to change the phase into an amplitude. Frequency modulator, we usually have a signal like this. So this is the phase. So the frequency is the derivative with respect to the time of the phase. So it's not easy to change the frequency of a signal. You cannot change the frequency. You can change the phase. Yes, frequency is the derivative of the phase. So if you change the phase, you change the frequency. But it's not easy to realize a frequency modulator. To realize a frequency modulator, you need to touch the device who generates the light. So the only possibility is to use a directly modulated laser. So this kind of device. A laser generated the light at a given frequency because the characteristic of the laser, the length of the cavity, the material inside, etc. So you have to change the cavity, you change the laser in order to change the frequency. So you cannot use a scheme like this to generate a frequency modulated signal. You must use this one and change the characteristic of the laser. Now, every time we talk about modulation, it means that we have in mind the transmission of the information, so a link, so the transmitter and the receiver. So you cannot think just to the modulator itself, you have to think to the receiver, because then you have to receive the signal. And if the signal is amplitude modulated, frequency modulated, phase modulated, the receiver is different. So it does not make sense to think just to the modulator itself, but you have to think to the entire system. So this is not really the topic of this course, but you have to have in mind this problem. So if you have an amplitude modulator, you change the amplitude, the receiver, the simplest receiver, is just a photodetector, a photodiode. A photodetector detects the intensity of the light, so if you change the intensity of the light, the photodetector reads the information itself. If you have a phase modulation, then you need a phase demodulator. So